All right, good morning, everyone. Okay, let me start by sharing my screen. All right, we've been looking at aldehydes and ketones. And just a quick review of nomenclature. All right, aldehydes will end with the suffix al. Right, so this is methanal. This one would be butanal. Okay, and so on. The aldehyde group takes priority over alkenes, alkynes, amines, alcohols, and ketones. Okay, an alcohol as a substituent is a hydroxy. A ketone as a substituent is an oxo. This is 1, 2, 3, 4, 5. This is pentanal. Pentanal, and it would be 4-oxo. Okay, not oxy, but oxo. Okay, the aldehyde group is understood to be on carbon number 1. Right, if we have a cyclic aldehyde, okay, this would be named as cyclohexane carbaldehyde. Again, cyclohexanal implies there's only 6 carbons, but there's 7. And so this carb takes care of the extra carbon. Cyclohexane carbaldehyde. Right, in this case, the point of the ring in which the aldehyde group is attached, this is carbon number 1, unlike an open chain aldehyde. Okay, so this would be 4-hydroxy. 4-hydroxy cyclohexane carbaldehyde. Okay, unlike an aldehyde, a ketone functional group can be part of a ring. So this is cyclohexanone. The ONE ending indicates a ketone. Okay, if a ketone is a primary functional group, then it ends in ONE. And in this example, it's understood that the ketone is on number 1. Okay, in this case, we would have to number the ketone functional group location. So this is hept. Here we have 7 carbons. And this would be hept 1-ene 4-one. Hept 1-ene 4-one. The older method of naming would be to say 1-heptene 4-one. The newer method places the number right before the infix. All right, if we have 2 ketone functional groups, then it's a dione. Okay, so this is 1, 2, 3, 4, 5, 6, 7 heptane 2, 5, 2, 5 dione. Okay, dione 2 ketone groups. All right, many aldehydes and ketones have widely used common names. Methanal is more commonly known as formaldehyde. Ethanal is more commonly known as acetaldehyde, and propanone would be the IUPAC. Okay, we could say 2-propanone, but in this case the ketone has to be on number 2. Much more commonly called acetone. That's the simplest ketone. Here are some other compounds that have widely recognized common names. Acrolein is 2-propenal. Acetophenone, methylphenylketone. Benzophenone, diphenylketone. Okay, again, this is the order of priority. Okay, this doesn't have all the functional groups, but carboxylic acids are way up at the top, then aldehydes, then ketones, then alcohols. Another way of naming ketones, which I alluded to in an earlier slide just a moment ago, is to name the 2 groups on either side. Okay, so this first one down at the bottom is methylethyl ketone. We have diethyl ketone. We have dicyclohexyl ketone. So this is another way of naming ketones. These are common names, but they're still widely used. Okay, the main point here is the carbonyl has a large dipole moment, and so these compounds are subject to dipole-dipole forces, and this raises both their boiling points and their solubility in water. Okay, not as much as alcohols of similar molecular weight. Alcohols can exhibit hydrogen bonding as well. So if we compare something like 2-butanone with 1-butanol, okay, we can see there's a noticeable increase in boiling point for the alcohol. For carboxylic acids, there's even a greater. You have more sites for hydrogen bonding with a carboxylic acid. Okay, but aldehydes and ketones have higher boiling points than alkanes or ethers of similar molecular weight. All Okay, because of the large dipole moment of the carbonyl and the ability to accept hydrogen bonds, lower molecular weight aldehydes and ketones are highly soluble in water. As the size of the alkyl group increases, solubility goes down. Okay, and then this is what we were talking about when we left off. We looked at a few examples of this. Okay, this is the most common type of reaction for aldehydes and ketones. It's called nucleophilic addition. Right, the nucleophile adds to the carbonyl carbon, pushes a pair of electrons up onto the oxygen. We go through this tetrahedral intermediate, and then there's a second step where the oxygen undergoes protonation. Okay, Grignard reagents are alkyl or aryl magnesium halides. Okay, these were named after Victor Grignard. If you take an alkyl or aryl halide and react it with magnesium metal, and it turns out the solvent is important. Ether is the most commonly used solvent. The other one is THF, which is another type of ether. Magnesium inserts itself between the carbon and the halogen. Okay, this completely reverses the polarity of the carbon. Okay, here in bromobutane, the carbon had a partial positive charge. Okay, the halogen's pulling electron density away. Okay, and that's why we can do SN2 reactions on these halides. Here, however, the polarity is reversed. Okay, now carbon carries a partial negative charge. Okay, so it becomes like a carbanion, a negatively charged carbon. Grignards are very strong bases, and so we want to make sure we exclude water, alcohols, or any of these other functional groups that have acidic hydrogens. Okay, what will happen is you'll simply get protonation at this carbon. You get the alkane, and then the reaction's over. Okay, this is okay. Backing up for a minute, this reaction is usually not useful, except when, okay, say we want to label a position with an isotope, we can use deuterated water to put a deuterium there, but in general, this is not useful. We want to be very careful to exclude water. Okay, so this will attack the carbonyl, will form a new carbon-carbon bond, and then when this reaction is complete, then you add dilute acid and you get an alcohol. Okay, formaldehyde gives you primary alcohol, other aldehydes give you a secondary alcohol, and ketones will give you a tertiary alcohol. Just a minute here. Okay, let me reshare. Okay, this is a little something to help remember the Grignard reaction. And I've actually had a couple of medical students tell me later on that they remembered this song and it helped them on a test. Okay, this can go to the tune of America the Beautiful or Gilligan's Island. The carbonyl is polarized, the carbon end is plus. The nucleophile will thus attack the carbon nucleus. A Grignard makes an alcohol of types there are but three, and forms a bond to correspond from C to shining C. Okay, working backwards, in other words, this is the alcohol, and how do we make it using a Grignard? Okay, remember we form a bond from C to shining C. We form a new carbon-carbon bond. So we locate the CO bond, we break the next carbon-carbon bond. The part without the oxygen becomes our Grignard. The part with the oxygen, we make that a double bond, we take away the H, and that becomes our carbonyl, our aldehyde or ketone. Okay, hemiacetal is defined as a molecule that contains both an alcohol and ether on the same carbon. Most hemiacetals are not favored in an equilibrium, with the exception of 5- and 6-membered rings. Okay, in that case, the hemiacetal is the dominant species at equilibrium. But in general, hemiacetals are not stable. Right, an acetal has 2 ether groups on the same carbon. Okay, here's an example of a cyclic hemiacetal, which we saw before. Once we get a hemiacetal, okay, what we can do is we use a strong acid, usually something like dry HCl gas or toluene sulfonic acid, something with very little water. Okay, so this protonates the oxygen, water leaves, and then the second equivalent of alcohol attacks, and we lose a proton, we get the acetal. Okay, in contrast to hemiacetals, most acetals are stable. The reaction is reversible. Okay, if we provide acid and a lot of water, then the acetal can be converted to back to the aldehyde or ketone. Right, here are, okay, let me show you these again. We can make cyclic acetals, 5- or 6-membered rings using diols. Okay, so here we have cyclohexanone. Okay, shortcut here, let out water. Okay, and that gives us this cyclic acetal. Acetals are good protecting groups. Since they are ethers, they're resistant to various reactions, including Grignard reactions. We could not do a Grignard with with this reaction because, of course, the bromine would interfere. Okay, but if we first make the acetal, okay, then we can make the Grignard, and then when we're done, we can remove the acetal protecting group. Okay, new topic here. Okay, we've looked at carbon nucleophiles, okay, like Grignard reagents. We have looked at oxygen nucleophiles, alcohols. Okay, now we're going to look at nitrogen nucleophiles. In the case of nitrogen nucleophiles, the product is a little bit different. The intermediate is not stable, but unlike a hemiacetal, instead of going back to starting material, what it does is it loses water, and we end up with a compound that has a CN double bond, which is called an imine. We start with ammonia. Okay, we'll get an imine. We can also use primary and secondary amines to form imines. Imines are also called Schiff bases. Okay, so what happens is we lose water, we lose 2 H's and an O, and we replace the CO double bond with a CN double bond. Okay, we lost 2 hydrogens to split out water, so we have 1 remaining. Right, so the amine will attack the carbonyl. We have a proton transfer from nitrogen onto the oxygen. Oxygen grabs that hydrogen. And the reaction doesn't stop there. Okay, that oxygen then picks up another proton. You have a trace of acid present. Okay, and then water leaves. We have removal of a proton. We get our imine. Right, this is an important reaction in fission. Cis-retinal, okay, which is a metabolite of vitamin A, reacts with this protein called opsin. Opsin has an NH2 group. It forms this imine called rhodopsin or visual purple. Okay, this is a reaction called reductive amination. My spell checker always has fits with the word amination. It always tries to convert it to animation. Okay, and this involves the formation of an imine followed by its reduction to an amine. Okay, so if we form an amine, an imine, there's various ways we can reduce it. For example, we could use hydrogen and nickel as a catalyst. Okay, this is in brackets because we don't isolate this. We combine everything. We do it all in one reaction vessel. Okay, so we make the imine and then we add a hydrogen to each side to get the amine. Okay, so reductive amination can convert ammonia to a primary amine and a primary amine to a secondary amine. All right, an enol is It's a compound that has an alcohol directly attached to an alkene. Enols usually are not stable. Let's see, for example, okay, here's acetaldehyde. The percent enol at equilibrium is 6 times 10 to the minus 4th percent. Okay, so it's very little of this, almost all the ketone. And for several of these others, again, the enol is not favored. Okay, there is a very small amount of this at equilibrium. These are not resonance structures because the hydrogen has been moved. Okay. So here, okay, we can have 2 enol forms. This one. And then there's this one. Okay, letter B would be similar. Okay, letter B below. Okay, this ene-diol, this is called an ene-diol. Okay, if you go on to take biochemistry, this is an important intermediate in not this particular compound, but this functional group is an intermediate in some of the sugar reactions, carbohydrate reactions. Okay. Right. So here you'd have this this ketone, this dione. Okay, this is this equilibrium is called tautomerism between a ketone and an enol. Okay, this is how it takes place with a little bit of acid. Okay, first of all, you have protonation of the oxygen, and then you have removal of an alpha hydrogen, and that gives you the enol. Okay, all these steps are reversible. Okay, because of keto-enol tautomerism, if there's a chiral center with a hydrogen adjacent to an aldehyde or ketone, we can have racemization that takes place with just a little bit of acid catalyst. Okay, this could lose its optical activity as half of it is converted to the other enantiomer. Okay. Right, aldehydes and ketones that have alpha hydrogens can react with bromine and chlorine to give an alpha haloaldehyde or an alpha halo ketone. Right, so here, this is done in acid solution, and okay, it turns out this, because it is an acid solution, we only replace one of the hydrogens. We have a CH3 here, and Okay, alpha bromoacetophenone is the product. This is also, this happens to be one of the components in tear gas. It's a very irritating substance. Okay, so this is how that takes place in acid solution. Okay, we convert a small amount of the ketone to the enol. Oxygen pushes down. The alkene picks up a bromine. And then we have deprotonation to give us the alpha halogenated carbonyl. Alpha halogenation is useful in that we now have a good substrate for SN2 reactions. For example, this amine can undergo an SN2 with this alpha bromoketone to give this substituted product. Okay, let's look at oxidation next. In an earlier chapter, we looked at oxidation of alcohols. Primary alcohols can be oxidized to aldehydes. If we use PCC as our oxidizer, we can stop at the aldehyde. But if we use chromic acid or KMNO4, it goes all the way to the carboxylic acid. Okay, well, it turns out that aldehydes are very easily oxidized. They're one of the most easily oxidized of all functional groups. You can use a strong oxidizer like chromic acid, and okay, that converts the aldehyde to a carboxylic acid. Turns out that even oxygen in the air can oxidize many aldehydes to carboxylic acids. Okay, this is a reaction that I've seen over the last few years in the laboratory. We've used benzaldehyde as a starting material, as a reagent in a synthetic reaction. And if the students don't get the lid on tight, or they forget to put the lid on, over a period of an hour or so, this starts to convert to benzoic acid. Benzaldehyde's a liquid, and it becomes a solid. Benzoic acid's a solid. So I've seen where the lid doesn't get on tight, and the bottle of liquid benzaldehyde turns all the way to solid. Okay, we can also oxidize aldehydes with just silver ions. And this produces a silver mirror on the test tube, as silver +1 gets reduced to silver 0. Ketones are much less subject to oxidation. They're not normally oxidized by chromic acid. Okay, if we oxidize secondary alcohols to ketones, okay, generally the ketone is not further oxidized, but ketones can be oxidized under severe conditions like hot nitric acid or hot KMNO4. And here's an example. Okay, notice what happens here is the ring actually gets opened. We get 2 carboxylic acids. So cyclohexanone is converted to hexane dioic acid or adipic acid. And then there's a note down here. Adipic acid is one of the starting materials for making nylon 6,6. Okay, here is the silver reaction that I was talking about earlier. Okay, if we take silver nitrate in ammonia, this is done in basic solution. The silver is very tightly, silver ion is very tightly complexed by the ammonia. Okay, balancing charges, silver is +1, ammonia has no charge, so this complex has a +1 charge. Okay, if there's an aldehyde present, okay, what happens is the aldehyde gets oxidized, the silver gets reduced to silver metal. Okay, next we'll look at reduction. Aldehydes are reduced to primary alcohols. Okay, remember a few chapters ago, primary alcohols were oxidized to aldehydes, so this is going the other direction. Ketones are reduced to secondary alcohols. Okay, what are some of the ways that we can reduce aldehydes and ketones? Okay, one way is catalytic hydrogenation. Okay, this is done at room temperature, 2 atmospheres. Okay, these are conditions that could be done in the laboratory, 1 to 5 atmospheres of hydrogen. Use thick-walled glass. If there's an alkene group, okay, shown here, okay, both of these groups are reduced under conditions of hydrogenation, both the carbonyl and the alkene. In fact, the alkene is usually a bit easier to reduce than the carbonyl, but we can reduce both these groups. Okay, most commonly though, if you're reducing aldehydes or ketones to alcohols, in the laboratory, instead of hydrogenation, more commonly we'll use these reducing agents, sodium borohydride, NaBH4, or lithium aluminum hydride, LiAlH4. Okay, the clue here that these are reducing agents is the high hydrogen content. Okay, these have lots of hydrogen. Okay, remember, oxidizing agents will have lots, many of them will have lots of oxygen. Okay, KMNO4, CR04, okay, lots of oxygen. Reducing agents will tend to have lots of hydrogen. Right, so sodium borohydride reductions are most commonly carried out in aqueous methanol, pure methanol, or in ethanol. Okay, the stoichiometry is 4 to 1. So we have 4 hydride equivalents. Let me back up a slide here. Okay, the active species here is the hydride ion. So each one of these delivers 4 hydride ions. Okay, so one equivalent of sodium borohydride will reduce 4 equivalents of aldehyde or ketone. Byproduct would be borate salts. Okay, so the key step is the transfer of a hydride ion. Okay, so this actually follows the same pattern as the Grignard, except instead of a carbon, it's a hydrogen that's acting as a nucleophile. So hydride adds, and then O minus picks up a proton from water, and we got our alcohol. Okay, so this hydrogen comes from the reducing agent, and this hydrogen comes from the solvent. Metal hydride reducing agents do not normally reduce carbon-carbon double bonds. Okay, so we can selectively reduce just the carbonyl and not the alkene group. Okay, this last reaction shows what we can do if we want to reduce just the alkene. Okay, we can form a protective group on the ketone, an acetal. Okay, we reduce the alkene by hydrogenation, and then we remove the acetal using dilute acid. Okay, and that concludes this chapter. I'm going to go ahead and stop there. Okay, and I will see you on Wednesday.